Hi guys, and welcome to the third in the chemical monitoring and management video series. For this particular one, we're going to look at a specific example of a chemical reaction which is useful to monitor, and it's one that you're very familiar with. It's the combustion reaction. There's a number of reasons why this whole topic is about monitoring and management. And so the context setter, I guess, where we start to actually look at some different types of reactions is when we start to discuss why we should monitor reactions. And obviously, one of the most important reasons that we should monitor reactions is for safety. We know that certain chemicals are flammable, and sometimes they are more flammable when they're combined with certain other chemicals. Some are corrosive, some are irritants in our mucous membranes or in our stomachs, and for that reason we need to make sure that we are always monitoring reactions to ensure safety for all of the people concerned. That's one of the reasons why we sort of suggest you should always be washing your hands after you've been working in the chemistry lab. So safety is probably the most important reason for monitoring reactions, but it's certainly not the only one. A lot of industrial chemists will be looking at monitoring reactions in order to increase yield. So by understanding something about a chemical process, we may understand how by varying the conditions under which that reaction is occurring, we may be able to change the amount of product that we're able to gain. Of course, this has particular important implications in things like mining, where there is a cost factor associated with the whole process of mining a particular ore from the ground, of refining that ore back into, first of all, removing it from any of the other parent rock that's around, and then to actually carry out whatever processes are required to purify the particular element that you're interested in that's part of that particular ore body. And depending on what's happening economically, supply and demand, a lot of economic rationales for why certain types of processes might be cost effective or not. And sometimes it's the processes themselves or the ways that those processes can be used. The use of things like catalysts can often be expensive, but they can also produce a similar yield in a much shorter period of time, and therefore over a given time frame you still will end up with more product. So these decisions have to be made, and also good reasons for monitoring reactions. Certain chemical reactions, even when we are extracting products that we want, may also yield certain waste products. And if those waste products can't be collected or can't be stored, they are often released into the environment, and that can have some fairly significant detrimental effects, particularly if we release them into the air, into the atmosphere, or into our waterways, water systems. They may even make their way into the food chains and can potentially obviously affect us. So levels of certain heavy metals, for example, in waterways where there are fish, where people may eat the fish, and even if people don't, some of the animals in the area may rely on aquatic organisms for food, and as a consequence you can have fairly significant effects if you're not keeping an eye on what sort of things are being dumped out into the air or into your waterways. And I guess one other reason for monitoring reactions is the fact that there are certain types of chemical reactions where the actual chemical nature of the products can change depending on what conditions you have. And the most important example that we're going to be looking at in this video is the example of combustion reactions. Depending on the level of oxygen, the particular products of the reaction can change. So we get different products depending on how much oxygen is present, and this gives us a very good reason for monitoring oxygen levels and ensuring that we make sure that we're maximizing our desired products and minimizing the ones that we don't want. So let's have a little bit of a look at some of the reasons why combustion is worth focusing as our example in this video. In a laboratory, methane is the key fuel that's used to light the Bunsen burners, for example, is a component of natural gas, one of the most important components of natural gas, and it burns efficiently and produces a good amount of energy per mole, kilojoules per mole. But it also can release different products depending on the amount of oxygen that's available. At low oxygen levels, there's a high soot production that creates particulate matter, which can be introduced into the atmosphere. And the problem with that, of course, is it can then increase the levels of pollution, at least locally. And so there may well be industrial chemists or chemists employed by car companies to look at ways of improving the efficiency of the fuel source. Of course, if we're talking about a car company, we might be talking more about something like ethanol or octane as the fuel source, but the principle is still the same. Getting complete combustion to occur reduces those more dangerous products like carbon and carbon monoxide from being released, and it may also be an issue relating to compliance, whether or not a particular organisation is actually being compliant in terms of their release of pollutants into the atmosphere. And this also has implications for things like global warming and carbon emission targets and those sorts of things. So our industrial chemist that's working is probably going to be using some sort of data logger or a probe, an oxygen sensor or a carbon dioxide sensor to monitor the levels of output from the car. We're going to look at a simpler example, that of the Bunsen burner, and we're going to focus on methane because it's just easier to demonstrate what's happening with these reactions when we just focus on one particular chemical, and that's why I've chosen to focus on methane in this particular video. Now, in natural gas, you may have some traces of ethane and propane in there as well, but we'll ignore them for the time being. And when the Bunsen burner is on, it's oxygen from the atmosphere that's actually being taken out and being used or consumed during this combustion reaction. So how much oxygen there is, or the availability or concentration of oxygen, is going to affect the products that form, whether we have carbon as soot, whether we have carbon monoxide or carbon dioxide as our products being formed. So there's two forms of incomplete combustion. In the first form of incomplete combustion, in very low oxygen environments, solid carbon or soot is formed. And you will have seen this with the Bunsen burner before, beakers that are heated on the orange flame, which is the lower temperature flame, with a hole closed, and that closed hole prevents some oxygen from entering into that region where the gas is igniting, and as a consequence the oxygen levels are low, and therefore we often see black test tubes or beakers as a result. That carbon soot, that solid carbon, is being deposited on the outside of the object being heated. If we increase the levels of oxygen, then what we may do is add oxygen into that carbon soot to produce carbon monoxide. And you can see here's the equation for incomplete combustion, where the levels of oxygen are just slightly higher than they were previously. But if we get the production of carbon or carbon monoxide, we're still in a low oxygen, low to moderate oxygen environment. So we're not getting complete combustion. In order to get complete combustion, we need to be in an environment which is oxygen rich. So where there's an excess of oxygen, plenty for this reaction to occur. And therefore, you can see with the extra oxygen, we now have carbon dioxide as our product. Now, it's worth, when you look at these types of reactions, having a look at the mole ratios. Okay, it's something that we've been looking at before with a lot of our reactions. And we just transfer the coefficient out the front, and if there isn't one, we just assume it's 1, 2, 1, 2. These are our mole ratios for the species that are present in this particular reaction. So that means that every mole of fuel, methane in this case, requires 2 moles of oxygen and will produce 2 moles of water and 1 mole of carbon dioxide. But how does that compare with incomplete combustion? Well, here's a table to give you, I guess, that picture a little bit more clearly. In a low oxygen environment, we have a ratio of 1 mole of fuel to 1 mole of oxygen. So just a 1-to-1 ratio. And you'll notice that that produces 2 moles of our water and 1 mole of our other product, which is the solid carbon in this case. In the second equation, we actually had a ratio of 2-to-3, which for simplicity's sake, I've reduced back to 1-to-1.5. So you can see as the amount of oxygen starts to increase, 1-to-1.5, we have the same amount of water being produced, but this time 1 mole of carbon monoxide being produced. Down to the last one, where the ratio of fuel to oxygen is now 1-to-2, so we have effectively twice as much oxygen being consumed in this last reaction as there was in the first one. The ratio is now 1-to-2, and again you can see still 2 water molecules being produced and just the one other product, which in this case would be carbon dioxide. Unlike the other couple of videos that we've looked at on specialized chemists and their work and the importance of collaboration, complete combustion reactions do come up from time to time. They're fairly straightforward, and you want to make sure that if you see a nice little 2-mark question that you store those 2 marks away. You just bank those because they'll be a nice, easy 2 marks. And this particular question from 2005 had 2 components to it, each of which was worth 1 mark. The first thing was that we needed to explain what the cause of incomplete combustion was, and that is, of course, low to moderate oxygen levels. Now you could put insufficient oxygen for complete combustion, but you just need to make sure that you have identified that there is insufficient oxygen in order for the carbon dioxide product to form. And then our next mark we get from writing a balanced equation for the incomplete combustion of methane. So I've already done this before, and you can pick either one that you would like. So if we start with methane and we combine it with oxygen gas, then let's just say we're going to form solid carbon soot as one of our products, and we will also produce water. And because of the temperatures associated with it, it won't be a liquid, it will be a gas. Then, of course, we've got to go through and make sure that our equation is balanced. And here we have 1 carbon and 1 carbon. Here we have 4 hydrogens, and 2 2s are 4 hydrogens. And over here we have 2 oxygens and 2 oxygens here. So our equation is balanced. These are fairly straightforward. Sometimes I'll be asking you questions that are associated with whether or not you can understand the importance of monitoring different types of reactions in order to determine what the products of those reactions will be. Thanks for watching.